gastrulation in chick. After the stage of blastula, where a epiblast and a hypoblast is formed, and in the center you have the blastocele. Then occurs what is known as gastrulation stage. Gastrulation, it begins within 4 or 5 hours after the onset of incubation. It's not after fertilization. After fertilization, the egg may remain intact. Once incubation starts, incubation or providing the apt temperature of 37 to 38 degrees centigrade to the egg, that process of incubation starts. Then development starts in chick and egg. And this development stage, the gastrulation, it begins within 4 or 5 hours after the onset of incubation, and it is completed by about 22 hours. So the stages that come from 4 to 22 hours, you call it as gastrulation process. And gastrulation in chick embryo, it can be divided into 2 phases: endoderm formation and primitive streak formation, and the movement of chorda mesodermal elements. We are learning a new term here, which is primitive streak, which is only found in chick embryo. And formation of endoderm, endoderm of hypoblast or hypoblast, it develops as a single layer of cells inside the blastocele. The epiblast splits into two. A blastocele is formed, and the lower layer is what you call endoderm or hypoblast. After the formation of endoderm, upper layer is called epiblast. There are different theories to explain the formation of endoderm. Infiltration theory, this was proposed by Peter in 1923. According to this theory, all these theories are based on how the hypoblast layer or endodermal layer is formed in chick. So according to this infiltration theory, it states that some cells in blastoderm which are loaded with yolk that will fall into blastocele that is formed. It starts from posterior end of the blastoderm. From there the cells migrate forward one behind another, and this results in the formation of an endoderm. Since it is infiltrating from the epiblast layer, it is infiltrating cell by cell from the epiblast layer. It is known as infiltration. Delamination theory, this was proposed by Spratt in 1946, where it is 2 or 3 layered thick blastoderm is present, and one of the lower layer that splits from the upper layer. So whole layer is split from the upper layer, and this splitting of layer is what results in endoderm. And upper layer are called ectoderm, the epiblast that forms the ectoderm, and the lower hypoblast layer that forms the endoderm. In between ectoderm and endoderm, blastocele is. Theory of involution. In 1909, Peterson proposed this theory. According to this theory, a slit-like opening at the posterior side of blastoderm forms. Through this opening, the blastoderm cells will roll into the primary blastocele. This forms an endoderm. So it is involution or moving in through an opening. Theory of invagination, this was proposed by Jacobson in 1938. According to this theory, the posterior end of blastoderm, it will invaginate or it will push in to this blastocele, a small pocket. This becomes endoderm. And theory of invagination says it is by this invagination or pushing that the endodermal layer is formed. This is how development takes place. 3 to 4 hours. These are the blastomeres. These are the pure transparent blastomeres that are formed, and these are the yolk-rich blastomeres that are formed. So this transparent clear-cut blastomeres, they form what is known as area pellucida. The area opaca, this is formed by yolk-laden blastomeres which are incomplete in division. And there you can see a thickened area of epiblast. And this region is what forms the primitive streak. So this is the anterior end, which is known as cephalic end, and this end is known as caudal end. So this is what is the condition at 3 to 4 hours, and at 10 to 12 hours a primitive streak is what is formed. So that is again the primitive streak from the posterior side, from the caudal side, it extends into the anterior side. The primitive streak what we called has now grown with ridges. Are formed on its sides. The primitive streak has ridges on its sides which are known as primitive ridge, and there's a groove. When ridges are there, obviously a groove will be there, and this groove is what is called primitive groove. At the anterior end, at the cephalic, doesn't reach the cephalic end, but it's growing towards the cephalic end, and the anterior end, it has a node like region which is known as Henson's node. There you have a pit which is known as primitive pit. This is the structure of primitive streak. Primitive streak is the arrangement of epiblast cells from caudal region to cephalic region, and this arrangement of cell forms what is known as primitive streak. The structure called primitive streak, it has cells arranged as in the form of ridge, and this ridge is what you call as primitive ridge. And within this primitive streak you have a groove which is known as primitive groove. At the anterior end of the primitive streak there is a pit which is called primitive pit, and this primitive pit is surrounded by few cells which are known as Henson's node. Formation of primitive streak, the second step in gastrulation, I told you it's a formation of primitive streak. First one, it is endodermal formation. Second one in gastrulation is the formation of primitive streak. At the posterior region of area pellucida, in the mid-dorsal line, primitive streaks appear as thickened area. It starts 8 hours after incubation. The thickening is because convergence of cells of blastoderm occurs towards this central point which forms the primitive streak. Early stages, the primitive streak is short and broad. It gradually extends to the middle of blastoderm. At 18 to 19 hours of incubation, primitive streak is well developed. It is called definite primitive. The mesoderm is formed as 2 layers in front of the primitive streak. An area without mesoderm is present, which is known as pro-amnion, and at this place the head of the future embryo starts to develop. After 48 hours of incubation, the pro-amnion is also occupied by mesoderm. The mesoderm is divided into dorsal and intermediate and lateral mesoderms. You have the cauda mesoderm. The mesoderm is divided into dorsal, intermediate and lateral mesoderms. The notocaudal cells, they arrange themselves to form a cylindrical rod called notocaudal process. It will begin at Henson's node and it slowly grows. Once primitive streak reaches its whole length, then the notochord starts to arise at the region in front of the Henson's node. Because of the growth of notocaudal process or the notochord cells, the primitive streak becomes reduced, and by the end of gastrulation the primitive streak is reduced and incorporate into tail bud. They form the tail bud of the embryo. So whatever region you have in front of the Henson's node, that forms into future embryo, and the region behind the region behind this Hensen's node that forms the extra-embryonic membranes. At 16 hours embryo, 16 hours after incubation, the primitive streak becomes so distinct that embryos are characterized as being in primitive streak stage. The primitive groove is lined by thickened primitive ridges. At the cephalic end of the primitive streak, you have the thickened area which is called as Hensen's node. Part of area pellucida adjacent to the primitive streak shows increased thickness and forms embryonic elliptical shape. Area pellucida assumes elliptical shape. Elongated primitive streak, it represents long axis of future embryonic body. Caudal end of the streak is that which lies close to the area opaca. So this is a structure. You have the caudal end here, the cephalic end here, the area opaca here, area pellucida is this area, and you have the primitive streak, primitive pit is there, primitive groove, primitive ridge, Hensen's node. And now when Hensen's node is completely developed, it starts to reduce. It starts to reduce and it gets reduced to half by 18 years, 18 hours of growth. Chick embryo. At this stage, the dark peripheral area opaca and central translucent area pellucida are distinctly visible. In the anterior part is present the pro-amnion, which is a small and comparatively more translucent region of area pellucida and is characterized by the absence of mesoderm. There in the pro-amnion you don't have the mesoderm cells. In the middle of area pellucida, in the posterior half runs a primitive streak having a primitive groove through its center. In the anterior half of area pellucida, in the middle runs a neural groove bound by neural fold. So you have 18 hours, you have both primitive streak as well as you have neural fold. And the primitive streak and neural groove is separated by thickening the Hensen's node having a small depression in the center, the Hensen's pit. The primitive streak gives rise to an outgrowth, the notochord immediately below this is at 18 hours. You have the halfway, you have the Hensen's node. From there you have the neural fold and a neural plate is also present. You have the, you can see the notochord. Then also pro-amnion is free of mesoderm. Area pellucida, it is clearly visible, and this area, this darkened area is what is known as area opaca. So this is the stage at 18 hours. The dorsal mesoderm is located on either side of notochord. It is divided into segments, and the segments, they are called somites, and the first pair of somites form after 21 hours of incubation. It starts to grow. The somites, a pair of somites start to grow when it is 20 hours of age, and by 21st hour a pair of somite is visible in chick embryo. Afterwards, for every 1 hour, one pair of somite will add. The 24 hours old embryo contains 4 pair of somites. The intermediate mesoderm connects the dorsal mesoderm with lateral mesoderm as a stalk. Afterwards, it undergoes segmentation and gives rise to kidneys. The lateral mesoderm extends on periphery of embryo and it is divisible into extra-embryonic and embryonic mesoderms. This lateral mesoderm, it will split into 2 layers. Upper layer is called somatic mesoderm and inner layer is called splanchnic mesoderm. They line the coelomic cavity. At later, ectoderm and somatic mesoderm will be called somatothure. That's a term we use for ectoderm plus somatic mesoderm, which is called somatothure. And the splanchnic layer or the visceral layer and the endoderm together is what is called splanchnoplure. The ectoderm and the somatic mesoderm or the parietal mesoderm together form the somatoplure, and they line the outer wall of the coelom, whereas the splanchnic layer and the endoderm, they line the visceral organs and are known as splanchnoplure. In between the two layers of mesoderm, the space is called coelom. Thus, at the end of gastrulation, specific organ forming areas start to develop. 24-hour chick embryo. At 24 hours incubation period, the chick embryo is oval in shape. The primitive streak is fully formed and the process of gastrulation is completed. The notochord, it extends from the Hensen's node as head process into the mesoderm free area anteriorly pro-amnion zone. The head fold and foregut develop in the embryo. The mesoderm differentiates into somites, and by 24 hours you will get somewhere around 4 pairs of somites. At this stage, the dark peripheral area opaca and central translucent and colorless area pellucida, they are distinctly visible. The anterior part is present, the proamnion, which is a small and comparatively more translucent region of area pellucida and is characterized by the absence of mesoderm. In the middle of area pellucida, in its posterior half runs a primitive streak with a primitive groove in its center. The primitive groove is bound by primitive fold. So this is the structure. You can see the primitive streak. 4 pairs of somites have arisen. You have the notochord in the center and you have the neural groove, and this neural folds have developed, and again proamnion is visible. And the ectoderm of head region is visible. You also see the foregut region. The foregut region, area pellucida is clearly visible and area opaca is darkly pigmented. Hensen's node is still present at 24 hours. In the 24-hour chick embryo, 4 pairs of somites are differentiated from the mesoderm. The coelom begins to develop in the lateral plate mesoderm. The blood islands appear in the area opaca. Pericardial region and primordial of heart are established. The area opaca further modifies into the area vacuosa and area vitellina. The neurectoderm, it gives rise to the neural folds and neural groove. The fusion of neural folds begin from the mid region. In the area pellucida, embryonic and extra-embryonic regions also become distinguished. In the anterior-most part of ectoderm has given rise to head fold, which is a pocket-like extension of neural fold. The underlying endoderm is also transformed into a pocket-like foregut, and proamnion that has now become greatly reduced. In front of Hensen's node, the mesoderm of embryonic area, it's differentiated into 4 pairs of mesodermal somites. The neural canal in the region of head fold has given rise to forebrain. The foregut extends on either side into an aminocardiac vesicle. Growth proceeds and reaches 33 hours chick embryo, lengthening of foregut and subcephalic pocket, formation of neural tube and sinus rhomboidalis. The primary division of encephalon into prosencephalon, mesencephalon and rhombencephalon takes place at 33 hours of development. Formation of neural crest cells on either side of the neural tube. Development of the infundibulum as a median ventral outgrowth from the floor of prosencephalon. This is the embryo at 33 hours. The primitive streak is very reduced. You have well developed brain, a spinal cord is also visible, and on either side you have somewhere around 11 to 12 pairs of 12 to 13 pairs of somites are arranged on either side of this spinal cord. Head is differentiated, brain is differentiated into prosencephalon, mesencephalon and rhombencephalon. The optic vesicle has started formation. Infundibulum is clearly visible. Formation of 13 pairs of somites. Development of heart as tubular structure lying in the mid-ventral region to the foregut. Formation of extra-embryonic blood vessels in the area vacuosa. Formation of intra-embryonic blood vessels. Disappearance of primitive. At this stage, the dark peripheral area opaca and central translucent area pellucida are not distinctly visible. The primitive streak has been comparatively reduced because of great lengthening of neural canal and neural fold. The extra-embryonic area that has grown in size, the mesoderm in front of Hensen's node, it has given rise to 11 to 12 pairs of somites. The mesoderm has split into nearly 13 pairs of somites. The foregut and cardiac vesicles are sufficiently developed. Proamnion has completely disappeared. Anterior omphalomesenteric vein has developed. 48 hours chick embryo, appearance of cranial flexion and torsion, formation of 11 neuromeres, 3 neuromeres in prosencephalon, in mesencephalon and 6 in rhombencephalon. Formation of secondary constriction in the brain, completion of vitelline circulatory system, which is extra-embryonic circulatory system. The blood islands are formed that join together to form an extra-embryonic or vitelline circulatory system. Development of intra-embryonic blood vessels start at 48 hours chick embryo. Formation of 2 pairs of aortic arches, twisting of the heart and formation of chambers. You cannot differentiate between area opaca and area pellucida. The extra-embryonic area, it has grown in size. Primitive streak completely disappeared. The mesoderm in front of Hensen's node has given rise to 26 to 28 pairs of somites. The brain has differentiated into telencephalon, prosencephalon, mesencephalon, meten and myelencephalon. The heart has been differentiated into ventricle and atrium, and you can see the beating of heart. Sinus venosus and truncus arteriosus have also started developing. The eye has been differentiated into optic cup, and lens and optic vesicle also has developed sufficiently. The head region has curved on right side due to cranial flexion. The neural development, the prosencephalon, a curving occurs, and this cranial flexion has occurred at 48 hours. 3 pharyngeal gill slits have also been differentiated, and behind Hensen's node a tail bud has also developed. Lateral amniotic folds, anterior omphalomesenteric vein and vitelline artery have appeared. So this is at 48 hours. You can see the head has started to bend because brain development has started, and brain development, 3/4 of the brain development has taken place. You can clearly see a heart with ventricles as well as atrium as well as sinus venosus and truncus arteriosus. And you can see about 28 pairs of somites on either side of the spinal cord, and the neural fold also extends up to this Hensen's node. And the primitive streak that is completely absent or it's completely disappearing at 48 hours. It is disappearing. It is changing itself into tail bud. Commencement of blood circulation takes place at 48 hours. Formation of optic cup and lens vesicle, formation of visceral cleft, development of auditory vesicle, development of extra-embryonic membranes, formation of pronephros. Fetal membranes of chick. The development of every vertebrate, certain tissues do not directly enter into formation of embryo proper. These tissues rather help in the care and maintenance of the embryo, and those membranes are called extra-embryonic membranes. In the development of chick, these membranes will develop from original blastoderm. The central part of blastoderm will give embryo proper. The marginal blastoderm will give extra-embryonic membranes. Amnion and chorion will develop from somatopleure. Yolk sac and allantois will develop from splanchnoplure. So we told about mesodermal cells. Mesodermal cells attached to ectoplasm cells as well as endoplasm cells. And from somatopleure develops amnion and chorion, while splanchnoplure, yolk sac and allantois develop from splanchnoplure. So this is the structure where you have these extra embryonic membranes. You can see this 4, that's the extra embryonic somatopleure, and 5, this is the extra embryonic splanchnoplure, and 6 is this 4 region between this 4 and 5 is what is known as coelom. Amnion and chorion. In the development of embryo, amnion and chorion are closely associated. Amnion is bag-like covering over the embryo. It separates the embryo from internal environment. Amnion is developed from somatopleuric amniotic folds. These folds are head folds, lateral folds and tail folds. And at about 30 hours of incubation, in front of the head of embryo, a head fold is developed. It is called amniotic head fold. So 33-hour embryo, when you are drawing 33-hour embryo, you can easily find this amniotic head fold. At about 3rd day of incubation, amniotic tail fold is developed. It grows opposite to head fold. Meanwhile, lateral folds will develop. They grow dorsomedially. So it is covered from all sides. The head fold is there, tail fold is there, as well as the dorsomedial covering of the lateral fold takes place. And after some time, head fold, lateral fold and tail fold will fuse near posterior end of the embryo. At 72 hours of incubation, they are still not fused. They show an opening which is called amniotic umbilicus. Afterwards, they unite. The amniotic folds consist of 2 limbs, an outer and inner, both consisting of ectoderm and a thin layer of somatic mesoderm. As the amniotic folds grow centripetally, they fuse to form continuous membrane which constitute 2 sacs around the embryo. So around the embryo you have amniotic layer membrane which is actually 2 sac-like around the embryo. And at the end of 4th day, embryo is completely enclosed in a cavity which is called amniotic cavity, bounded by amnion. The fluid is amniotic fluid or amnion. The space between the amnion and chorion is called zero amniotic cavity or exocele. The extra embryonic coelom is filled with a fluid. It gives protection to the developing embryo. The coelom gives space for developing allantois, and chorion combines with allantois and acts as a respiratory organ. Functions of amnion. Amnion is a sac-like structure around embryo. It contains amniotic fluid. It will protect embryo from mechanical shocks and desiccations. It protects the embryo when the egg is laid. It gives artificial aquatic environment for growth of embryo. It's a terrestrial one, so that moisture content is protected by this amniotic membrane. Yolk sac. At 16 hours of incubation, yolk sac makes its appearance. It develops from splanchnoplure, and the splanchnoplure, it contains endoderm and mesoderm layers. The splanchnoplure grows over yolk and becomes yolk sac. The primitive gut is present above the yolk. This yolk region is in contact with midgut. Finally, the yolk sac is communicated with midgut through an opening. So, the yolk sac has a connection with the midgut of growing embryo. The yolk sac is connected to the midgut by a narrow stalk called yolk stalk or umbilical stalk. The narrow canal within the yolk stalk is termed as the yolk duct. Yolk stalk is there and the canal is known as yolk. Functions of yolk sac: it digests the yolk and the digested food will be circulated through blood to the developing embryo. Hence, yolk sac is considered as a nutritive organ of the embryo. It also performs respiration through early development. Allantois in chick, it develops from the ventral part of caudal end of the hind gut. It develops at third day of incubation. About the third day of incubation, a region of the floor of the hind gut begins to bulge out as a diverticulum or an end sac, which gives rise to allantois. It consists of an inner endoderm and an outer splanchnic layer of mesoderm. Allantois remains posterior to yolk sac and expands rapidly, penetrating into the extra-embryonic. The distal end of allantois enlarges into an allantoic vesicle and the proximal part that becomes the allantoic stalk. The allantois arises within the body of the embryo at the hindgut region. The mesoderm of the chorion and mesoderm of allantois will unite. It forms chorioallantoic membrane. As the embryo is growing, the allantoic and yolk stalk are brought together. The mesodermal layers will unite. It is called umbilical stalk. It is covered by somatic umbilicus. Function of allantois: allantois is richly vascularized, hence it works as respiratory organ. It stores nitrogenous waste material of the embryo, and in later development the allantoic circulation will absorb calcium from the shell. This calcium is used in construction of bones in young ones. Allantois absorbs calcium from shell, hence the shell become thin. It helps in rupturing the shell during hatching. And 72-hour stage of chick embryo. At this stage, area opaca and area pellucida are not visible. The extra-embryonic area has grown in size. Primitive streak that has disappeared. The mesoderm in front of Hensen's node has given rise to 36 pairs of somites. The brain has differentiated into telencephalon, mesencephalon, metencephalon and myelencephalon. The heart has been differentiated into ventricle and atrium. The eye has differentiated into optic cup and lens, and optic vesicle has also developed sufficiently. The head region has bent on right side due to cranial flexion. 4 pairs of gill slits have been differentiated. Tail bud is greatly developed and has given rise to allantoic stalk and tail. Lateral amniotic folds, vitelline artery and anterior omphalomesenteric vein have developed. In the middle region, a pair of forelimb buds, and in front of tail, a pair of hind limb buds have developed, which will give rise to fore and hind limbs of the embryo. Olfactory pit, visceral arches, amnion, allantois and amniotic cavity have also developed.